you're going to use. So as these clean filters, they've got a certain differential pressure that they're rated at as they come from the manufacturer. As they begin to get dirtier and dirtier, this goes up maybe by as much as 20–25%, and that translates linearly into a 20–25% increase in power. So both of those things we're going to look at a little bit, and beyond the filters, I mean the coil is the same thing. It's obviously important to keep it clean. But what I want to talk about next is the idea of replacing these filters and making good decisions about what to buy. We used to do things just like everyone else did at one point. It's our maintenance people or whatever, they have a fixed budget, you know, so they're very conscious of what the products they're buying are have a first cost, so they would be really concentrated on first cost. And we started looking at that and trying to help them understand what the best products to buy maybe with respect to these, you know, to the energy performance of the thing. So we now use a life cycle cost approach to this instead of just looking at first cost. So what is the life cycle cost of a filter? It's really the first cost. It's the maintenance cost, which is this man's labor to change it and the frequency that he's going to have to change it. It's the energy costs associated with that filter, and finally it's the disposal cost. So I encourage you to look at really all four of those things. The energy costs related to a filter is routinely 10 times the amount of the initial cost, so it's critically important. How do you determine whether you're choosing a right filter or not? These things are rated according to a rating system called MERV. Whatever, so you're going to decide on a MERV rating, and the MERV is, another word for that is efficiency, but the word efficiency is used a different way than energy efficiency. It's the ability for the filter to remove particulates. So you're going to decide on a particular MERV rating that has an acceptable cleaning effect for your facility and your coil, and then you're going to start looking at this differential pressure, and these filters come with a rating system. And you're going to compare that, and I encourage you to do the calculations to see what your true cost for that filter is, comparing two different units. We went to, a couple of years ago when I was talking about when I was working with the maintenance guys, what we did was we went and looked at some of our large facilities, and they seem to all be made about the same way. They've got at that time they had a 12-inch box filter as the main filtration, and then before that they had a 2-inch cartridge filter like this gentleman's putting in. And so I found a product or 3M brought me a product that they started producing that's it's Filtrete. Has anyone heard of that product yet? Filtrete, made by 3M, yeah. And it's kind of a revolutionary air filter, and I'm not endorsing it, but I can tell you that we use it at UCF now quite a bit. And the difference, it looks just like these filters, but it has a built-in electrostatic charge into it. And so what they are able to do is make this filter media more porous, where it has a lower pressure drop across it, which translates into more energy savings for us. But at the same time, the electrostatic charge allows it to still remove the particulates of a finer filter. So we're getting the clean air without having the bigger pressure drop. And we've gone and now we've removed the 12-inch filters entirely. We don't use those anymore. They removed the 2-inch, and we installed the 3M product in the 2-inch rack in the front. So now that's the only filtration system for the units, and that's been working very well for us. The other thing that did for us, I forgot to mention, is that they were changing the pre-filters every 3 months, and they were changing the box filters once a year. Now we're able to do the 3M product by itself every 9 months. So it's been a big labor savings for us as well. Just a couple other things on filters. When you do change them, make sure you get the right fit, make sure they're the right size, they fit tightly, and make sure the cavity that they go into is obviously straight, clean, and you get good fit there. Without good fit, you see these spaces between the filters here going both X and Y direction that will tend to bypass air. So we seal that with a clear packing tape, just something real cheap. It's only going to be on there for 8–9 months. It doesn't come off pretty much. And then make sure your arrows are going in the right direction. These are asymmetrical products. Yes, sir.
You get about 9 months. How is that determined?
Yeah, it's measuring the pressure drop.
Okay.
It's exactly, we measure that in real time. Yep. This is another product that's real common in the HVAC field, and it's a great energy saver for us. I'm sure everybody's seen this, but I want to hit on it. This is called a variable frequency drive or variable speed drive. It's a little electronic box over here that actually, its job is to slow down the motors in the facility, but do it in a super efficient way. And there exists a really powerful relationship between fan speed and power that we take advantage of to save a ton of money. So we had that, well, here's the relationship, right? Power is fan speed and pressure drop. So this takes advantage of the fan speed part of it. And it's a cubic relationship, as you can see here. So if we can drop a fan speed by just 20%, that translates to a 50% reduction in power for us. This is much more powerful than even the filter thing is. And so if we take it to 50%, which we routinely do at night in our facilities, overnight we might be down in the 50s. 50% translates to a 87% power reduction for that motor. Scheduling is another really powerful tool. I'm sure that you're taking advantage of by now, but this is a product that's, I mean, these are available now at Home Depot, everywhere else for $30 or $40. This is about a $200 thermostat here that's more of a commercial model, and it gives you a little bit more freedom, but it'll hold multiple time schedules, so we can schedule this DX equipment. We can schedule not only the cooling, but also schedule the ventilation independent of each other, and take advantage of even additional savings. So for a 10,000 square foot facility, I estimate the HVAC costs to be about $12,000 a year. So if we can cut that by half or a fourth or whatever, we're talking about big dollars in an annual basis. Equipment efficiency. This doesn't apply to a lot of people, I understand, because it comes with a new facility, or it comes when you're redoing the components. But I think it's important, even year to year, as the efficiency advances come, that we keep mindful of that, because at some point we're going to need to, bite the bullet and do an investment a bigger investment in the facility. So this is an example of just 13 SEER right now is the minimum you can buy for HVAC equipment, and this is just one step up. If we just go one little step above the very bottom, least efficient thing you can buy, a 5-ton unit will cost you $500 more, and it returns itself 9 times over the life, 15-year life. Or for a commercial facility, looking at a $12,000 investment, $125,000 over the life of the equipment. It's really a powerful tool. So I encourage you to not to just wait until the end of life to start looking at that, and depending on how old your equipment is, start looking at those SEER ratings on the direct expansion units. Motor efficiency is another one that we've used a lot of this at UCF, replacing a lot of units based on these savings numbers. So this is just for a 5 horsepower unit, a relatively small motor for us. We can get it between a 2 and a 3 year payback, or 2 and a 4 year payback, depending on which unit. And I think we're mostly speccing the EPAC, which is the standard high efficiency motor, but we use some of the premium as well, depending on the horsepower. These efficiency ratings change quite a bit. So this is just applicable for a 5 horse. So I encourage you to look at whatever horsepower you're replacing, run those numbers and see what the payback really is. And don't forget to include both the consumption savings and the demand savings in your calculations, which is critical. Ventilation. This is a big one for us in Central Florida. Well, it's big because we're under the same regulations everybody else is, but it costs us a lot more to ventilate here than it does in other places because of our environment. So this is ASHRAE, the American Society of Heating, Refrigeration, Air Conditioning Engineers, sets a standard for this. It's pretty much used all over the country as the minimum code for building codes. And the standard has changed quite a bit over the years. When I first got in the industry, it was I think it was a flat 5 CFM per person at that point for just everything, and then all of a sudden it jumped to 20 CFM per person. Everybody in energy freaked out, and said, "You're going to end the world, ASHRAE." And so now they've got the latest version is taking into account not only people but also space. They have an option where you can look at your square footage and they allow you to get back down to 5 CFM if you account for the space as well. So the current is 5 and 60 CFM for every 1,000 square feet. So why do we want to ventilate for people? People exhale CO2 when they breathe, and that builds up in a space. So we've got to bring in ventilation to remove that CO2, that carbon dioxide. And for the rest of the building, we want to, because we have carpet, we have paint, we have everything giving off the volatile organic compounds that we need to exhaust out of the space. So that's why ASHRAE split it up here and allows us to look at it 2 different ways. And the problem with us in Central Florida is the water content. Obviously, we're bringing in a tremendous amount of water vapor when we bring in ventilation. And again, that's roughly about 80% of that latent load of that air handler that's seeing that is due to the ventilation air coming into it. These numbers here are our design conditions for Central Florida, and this is actually a very wet, as you know, you live here. You know there's a lot of moisture outside. So every 1,000 CFM we bring in generates about 3 gallons per minute of water that actually gets condensed into that condenser pan if your units look working right. And that process is called dehumidification. So we talked earlier about the air coming in mixed with water vapor, hitting a cold coil, condensing. That's our primary means for dehumidification. So that's why we're talking about nothing beats a cold coil. For every 100 people from the numbers on the last slide, the ASHRAE numbers, we need 500 CFM, and those people need about 10,000 square feet, 100 square feet each. So we need a total of 1,100 CFM coming into the facility to ventilate for those 100 people. And let's say TLC designed this job and it's working perfect, right? It's the middle of the day, nice and comfortable, and everything is perfect. And 5 o'clock comes and 90 people go home and 10 people stay there to finish up a project. All of a sudden, and we don't have any kind of setback in place, and all of a sudden what happens? We start overcooling because we lost that interior heat load in the space maybe. If it's not setting back, then it starts to cool down a little bit. And what happens next? We've got unhappy people. We face this every day at UCF, trying to work with this, trying to get the ventilation right and getting the so that we're not having to put in artificial warming means to keep the place warmed up. But you can't always do it, and we're going to talk about how you can maybe warm things up. But besides unhappy people, we also have humidity concerns when this happens. As the temperature drops in the space and the water content remains the same, the relative humidity rises. So we've got to be, it's another issue we face when we lose our heat load all of a sudden. So we're going to look at ways to prevent overventilation, and also what we can do when we can't prevent it, kind of thing. These are some means that we can control ventilation in our commercial buildings. And the first one is a time schedule. So if we had that building that we saw on the last slide, and we could have the schedule set by a thermostat or something that cuts it off at 5 o'clock, or it reduces it to half or something. That would be the example of a time schedule. Just running off a simple time clock can be very effective. But the problem with that is it's not adaptive. Whatever, it doesn't. When you do change your schedule, or people do have to work late or whatever, it doesn't really adapt to the facility very well. So there's other ways. There's occupancy based. Everyone's seen the aux sensors that we use for lighting control nowadays. It has a little infrared sensor on the wall. Those can be used as well for determining ventilation needs in a space. The idea there is we know the square footage, right? We know the furniture is still in there, but we don't know how many people are in there. So these other means are trying to figure out when there's people in there and when there's vacant areas. Another one might be a pollutant based, and that's an example of that is this meter here we have pictured here. This is a carbon dioxide meter, so if people are exhaling CO2 when they're there and we have a certain reading, we can translate that into a certain number of people or a certain need for ventilation. And the problem with this is that it gets a little tricky about where to place and how to